Okay, so who are we and what do we do? Spectrum Centre is a unification of the former ATDI offices, and we've got offices both in the UK, the US and Brazil. We're spectrum management specialists. Our flagship product, the product that you will see today, is Spectrum E. It's an off-the-shelf COTS product, and it's a SaaS solution, and it incorporates 3 modules, one for technical analysis, one for e-licensing, and remote measurement. Spectrum E can be modified to meet specific end-user needs. The flexibility of the platform allows modifications to be completed relatively easily to ensure the outputs are personalised to your own requirements. In addition, Spectrum Centre has a long history of providing consultancy services across a broad spectrum of technologies and markets. So, turning now to Spectrum E, which is our flagship product. Spectrum E is a browser-based product application, and it will, like I said, form part of today's demonstration. The key application features for that are the fact that it's supported both on a mobile, laptop or PC, and other platforms such as Mac and Windows. Spectrum is an HTML5 compliant software. Availability for hosting is in the cloud. You can have a local installation and also can be used in standalone mode. In terms of security, it features this SSL socket layer encryption. And stringent tests are applied during the development of the software, as the software is actually used by government and military organisations. So before I hand over, just the key drivers of the software, the simplification of the interactions with the software. We have an easy-to-use workflows and user interface. The standardized simulations provide a consistency of results. Improved performance, that's a radically reduced calculation times in terms of because of the result of the software architecture. And easy to use. So in terms of migration and adoption, that's far easier. Reduction in the requirement for any on-site training. And all of the modules have a sort of similar look and feel, which makes the adoption far easier. I'm going to hand over now to Daniel, who's going to take us through the rest of today's presentation. Over to you, Daniel.
Oops, my microphone is off. Thank you very much. I'm going to actually turn off my camera because it interferes a little with my screen. So I'm going to drive the presentation. I also have my colleague Quinny Huang, who is one of the lead developers behind the implementation of the 1812 model. And so at the end of the demonstration, we'll have a little bit of time for questions and answers. Just a little bit of a brief overview on radio frequency propagation models. I'm sure many of the people attending already know what this is about, but for those that maybe want to learn a little bit on the topic, we'll just have a very brief overview first, and then we'll get into the software demonstration. So what is a radio frequency propagation model? Essentially, the purpose of a propagation model is to help predict predict the coverage area of a radio emission. This is important for helping decongest RF signals, predict potential interference, and obviously implement measures to prevent interference. So as you see on the right here, there's an allocation chart. The idea is to allocate these natural resources, radio spectrum, in a way that you will avoid interference, and the prediction model, a propagation prediction model, helps with that. Governments around the world are refarming wireless spectrum to help find more available 4G and 5G spectrum as wireless broadband is growing at a very rapid pace. So go to the next slide. And radio frequency propagation models are used to predict path loss and power receive values for RF signals based on curves fitted to measurement data, statistical approaches, theories, or combinations of the three. RF propagation models help predict RF system performance for both wanted and unwanted signals. RF propagation models can be used to predict performance of planned RF systems, but also to analyze existing interference events. So the 1812 is one such model. It is part of the P series, radio wave propagation series from the International Telecommunications Union. The document is titled "A Path-Specific Propagation Prediction Method for Point-to-Area Terrestrial Networks or Terrestrial Services in the VHF and UHF bands." It was first published in November of 2007, and the latest revision, the -5, was published just last year, August 2019. It is applicable to frequencies in the 30 megahertz to 3 gigahertz range, and it would prove as a suitable model for point-to-area terrestrial networks with path lengths ranging between, say, 200 kilometers and under 1 kilometer. So what does that mean? It could be useful for broadcasts, analog, digital, FM, and TV. Mobile systems, mobile trunking systems in particular, operating VHF, UHF bands, such as land mobile radio, private mobile radio, tetrapole, professional services, this sort of thing. And also something that it's got a usefulness are what we call wireless proximity networks. These would be short-range networks, usually working in ISM band, 2.4, 2.5 gigahertz, so 3.5 gigahertz, 5.8 gigahertz. And usually these types of networks have relatively short range. We're talking about maybe a Wi-Fi network, IoT network. They're top between, a kilometer, maybe 500 meters for each access point or each point of presence. So that's a little unique. One other thing that's unique about this model is not just how it's able to have relevance to so many radio network applications, but also that it's coming from an international organization such as the ITU. Typically, the ITU is very focused on regulatory needs, and so the other propagation models are either addressing the needs of a regulator, such as, let's say, the 1546, or they're very what we would call deterministic. There's one called a very popular one named the 526, but it really only addresses one aspect of radio propagation, which is diffraction. Well, let's go into the inputs of the model, and then we'll go into what is the 1812 covering. So the inputs are frequency. It's got two variability inputs, percentage of average year for which the calculated signal level is exceeded, and percentage of locations, we call location variability, for which the calculated signal level is exceeded. Coordinates, latitude, longitude, antenna height, antenna center height above ground level, that'd be for the transmit and receive locations, and the signal polarization, vertical or horizontal. What the model covers are 6 following propagation mechanisms. We're not going to go into detail on each one. We have done other videos. There's one actually on the 452 that if you guys want to go on our YouTube channel, we have a little more in-depth discussion as to what these different mechanisms actually do, but I'm going to assume most of you already kind of understand it. So I'm going to go over them fairly quickly and then highlight some things that are unique about the 1812. So the 1812 model is what we would call a mixed model. It's not strictly deterministic in the sense that it's not only dependent or only limited to the use of the modeling environment that's provided to it, meaning the digital terrain and clutter data, but it also has features that consider what we call non-deterministic aspects, like let's say atmospheric conditions. So as you can see, it does obviously radio line of sight. It considers the free space loss. It considers diffraction, smooth earth, regular terrain, and subpath cases. And that would be kind of the limitation of what we would call deterministic to a degree. Also considering clutter heights would be in there, but we'll get to clutter heights in a little bit. Then the non-deterministic, or what we also call empirical aspects of the propagation modeling, are tropospheric scatter. So there's an example here in the diagram to the right. You see a little like scatter point. That's describing what is meant by tropospheric scatter. So the signal bounces off the troposphere and then reflects down into the terrain. at a longer distance than would be anticipated. There's also other anomalous propagation effects such as ducting, reflection and refraction, and then location variability and building entry loss, as well as height gain variation and clutter. So especially the atmospheric effects, the variability considerations, those are non-deterministic components of radio propagation modeling. And so the 1812 is one of the first recommendations from the ITU to straddle both sides in a way that is not overly, I'd say, conservative, you could say, or optimistic, you could say. There's been other models that are mixed models from the ITU, but they haven't been terribly relevant for network planning. What we mean by that, I'll get to in a moment. So terminal clutter losses. This is something very unique to the 1812 model. It was included in one of the more recent revisions, if I'm not mistaken. And what is meant by terminal clutter losses is actually the 1812 model has recommendations for clutter heights and recommendations on how to interpret the loss for those clutter heights. So you can see there's a criteria at the bottom here. If a height is going to be on the transmit or receive side is greater than or equal to R, that's the clutter height, then there's no loss assigned. There's no terminal clutter loss assigned. But if the height of the transmitter receiver is less than the clutter height, then there can be one of these attenuation formulas that are applied. And the attenuation formulas that are applicable depend on the clutter type. So you can see here, there's 5 clutter type considerations, which is pretty interesting. It's a little more than some of the other recommendations for clutter modeling that the ITU have provided in the past. And they have heights to assign to those clutter categories. One thing you'll notice right away is that it does give a 10-meter height to water, which was very unique, very interesting. But as we'll see, without using the clutter height terminal clutter loss option in 1812, it can be considered overly optimistic. And so we'll run through a few exercises later to kind of illustrate the point. But we have seen that when the terminal clutter losses are applied, when they're relevant, again, if your transmit and receive heights are very high, you might not be able to really see this benefit. So it's not a model for every possible application. But if your transmit and receive heights are below these heights, these clutter heights, then you might actually see a result that is maybe closer aligned to your expectations as an experienced radio network planner. So we're going to see that in action in a little bit. So getting back to one of the purposes of implementing the 1812 model is that it had a compatibility with highly granular digital surface models without ignoring non-deterministic propagation factors such as tropospheric scatter, anomalous propagation, location variability. I've got some screenshots here on the right, and as you can see, the software here is performing a prediction heat map using the 1812 model, and it's working with a 1-meter LiDAR DSM, digital surface model, that contains discrete heights for building and tree elevation data. So that's very unique, that the model has this level of compatibility. Of course, there's many proprietary models that have been developed over the years that can achieve the same ends, but coming from an international regulatory source, and also we're going to go over a little bit, being a verified model, meaning the ITU provided some source code, and they also provided some benchmarking, baselining data to the public. That is taking a step toward what we could say eventually kind of having people or having the industry be able to kind of standardize their propagation approach and not be dependent on a proprietary solution for that. Because the more people have their own unique ways of achieving a propagation, radio propagation simulation, the the more difficult it can be to reproduce it amongst various groups or entities. So you can get this kind of conflict. That's not to say that it is a standard. ITU, none of the ITU recommendations are standards necessarily, they're recommendations, but the ITU gave a good amount of information to try and get everyone on the same page when they go about implementing the ITU 1812. So, so this is very unique. This is probably the first ITU recommendation that is designed to work in this kind of manner, to work with highly granular data, meaning it's kind of designed for modern computing systems that can take this amount of information and process it. Another thing that's considered in the 1812 model are radioclimactic zones. So there's 3 zones that are defined. Zone 1 is sea, zone 3 coastal land, 4 inland. And those zones were included into Spectrum E. As you can see, there's a screenshot on the right. And we produced these zones from the ITU Digital World, I think it's Digital World Map, if I'm not mistaken, the IDWM. So we applied the criteria that's defined for each zone. So seas, you can read the criteria. It's any area covering a circle of at least 100 kilometers in diameter. The more interesting criteria was the coastal land. So the definition of a coastal land radioclimactic zone, according to the 1812, is that it's a land adjacent to the sea up to an altitude of 100 meters relative to mean sea or water level, but limited to a distance of 50 kilometers from the nearest sea area. Where precise 100-meter data is not available, an approximate value may be used. So that is also included. It's an extra layer of mapping information that the 1812 model can take advantage of if made available, and it is available in Spectrum E. So that's good. And the verification. So we did a C++ language implementation of the 1812 model, and we compared it with the MATLAB implementation that was obtained from the ITU Study Group 3 website on software data and validation examples. So we analyzed a set of terrain profiles, and we were able to compare those profiles between the C++ implementation and the MATLAB implementation for 3 different time percentages, 1%, 10%, and 50%. And I don't have like some statistics out here, but you can see the results were very similar out to a lot of cases the 4th decimal degree. So that's very good. There's a lot of consistency that allowed us to baseline the implementation. I think the profiles are mostly done in the UK. So obviously it wasn't done for every possible area. We know different parts of the world operate a little differently, but it is at least some baselining to help any developer or implementation team that wants to implement 1812, give them some guidance on how about to do some sanity checking and baselining of their implementation against kind of a neutral source. So that was, went very well, and so we have then since then been using the 1812. Our customer base has been using 1812 with different environments and giving us more feedback. So with that, I'm going to skip into the software part of demonstration. I'm going to log out here just to show the first part. So this is Spectrum E. You can go to Spectrum E by simply entering spectrum.center. You see I have a secure connection, so you can be safe to know that the connection to our server is secure. If you want to request an access, you can just click on the request access link, and then this can allow us to receive a request for a trial. If you want to trial the technical analysis module, so enter your name, email information, click on request technical analysis module, access, enter in a little message, usually a phone number or something like that would be good, and then we'll receive your request, and then we can proceed to authorize to give you a trial. If you are satisfied with what you've seen after this demo, you want to subscribe right away, you can always click on the subscribe option, and you can pay with a credit card. The 1812 model is included by default with the unlimited option, but if you don't want to get the unlimited option, we have other pricing options and you can just contact us at sales@spectrum.center, and we can try to accommodate you. Okay, so I'm going to log in. I have my credentials, and I'm going to go in. As you can see, this is all running off a browser. So everything's going to run off a browser. It doesn't have to run online. You can download SpectrumE. There's an option right here to download SpectrumE, and there's instructions to have a local copy. So it takes a couple hours to get it all installed locally, get the whole web stack, get some mapping data, etc. But you can download it locally and run it locally. And that can also be done under the SaaS model, the software as a service model, or of course perpetual licensing. So I'm going to jump over to my network page, and I'm going to probably jump into an example that I had already created in the past. So this is a map of a network in Crete that I'm going to highlight. So here is the map of Crete, and here's a little network there. And here's my map interface. And as you see, I zoom out, I can see the whole planet. So one nice thing about SpectrumE is you have worldwide cartographic data at your fingertips right away. No need to import data, manipulate, massage it, convert it, or load limited area data sets. You get everything, including the terrain and clutter. I'll highlight that in a moment. So you've got global terrain. This is at 30 meters for anywhere in the world. And you've got clutter or land cover for anywhere in the world, 30 meters as well. Now, we do offer higher resolution at certain places. We try not to work too much with proprietary clutter sources, but there are options in the tool to load a proprietary data set if you wish, or a private data set, especially if you want to work in the offline mode. So that's an option that exists in the tool as well. But usually we're working with either USGS or NASA or Korean land cover or EU data. There's a lot of public sources for clutter and terrain data around the world. So I'm going to go ahead and go to the terrain view. Oops. Oh, and the coastal zones. I'll highlight that actually. Here we go. So we got the coastal zone view, as you guys could see what I showed earlier. So what I'm going to do is actually I'm going to go back to my map layer. And we have map and photo as well. So we have a satellite photo layer. As you can see, you can stream in the photo information, changing your rate, your zoom level. So I'm going to go ahead and change this to my map and go out. So you see I have a network here. I want to just do a couple profiles, which I'd actually generated already. And I did one with the 1812 model between 2 points. Actually, let's do this one. One nice thing about the tool is that if I create two profiles, I can have them opened up into different browsers so I can compare one against the other. So here's, I wanted to compare one model. Here is, let's go back to the 1812. And let's do this without the thermal clutter losses. And you'll be able to see that it creates its path profile calculation. The red curve here represents the free space loss. And you can see the loss value changes as I move my cursor over the map. Then you have in the bottom the path loss calculation. It's the orange curve. It'll be the orange or green curve in the tool. Then the line of sight, and then you'll see the free space loss. So this is like a VHF, I think, band emission, or UHF 400 megahertz. And you'll see the amount of model loss, 175. And if I were to compare it with another model, let's say the 526, we'll see probably there's about, I think, 28 dB difference in the calculation. So that's what we meant, or what I meant when I said it's considered very optimistic until I apply the terminal clutter losses. When I do that, see that the result is very close to some other well appreciated models, we could say. So I have a 203 dB loss. It's not to say it's better or worse, either models are better or worse, but there's some that are just generally appreciated for RF network planning. And this is kind of approximating it. And again, you're not sacrificing the non-deterministic aspects. You're not ignoring location variability. You're not ignoring troposcatter. You're not ignoring ducting, anomalous propagation, building entry loss, things like this, where with a very deterministic model like the 526, you are ignoring all those components pretty much for the most part. Not to say it's wrong or right, but that is how the model is designed. It's a purely mathematical deterministic model. So you could compare, in the tool you can compare between a variety of different propagation modeling options. So I just wanted to highlight that. I'm going to go and actually switch networks. I've opened a number of browsers, I'm going to close them, and I'm going to switch to a project I have in San Francisco. And this project is interesting because I have not just 30-meter terrain and land cover data, I have high resolution data, what we call 1-meter LiDAR. So I'm going to switch to my terrain view. So this here is at the 30-meter layer, and as I move my cursor around at the bottom, it tells me the position information as well as the elevation information at that crosshair's position. And as I move closer, I'll see that there is a layer of additional information there. So the tool can toggle between either layer in the calculation, and I'll show in a little bit how that works. So in this part of San Francisco, I do have high resolution LiDAR data. So you can see here, it captures the building information. I'm going to overlay an image. Let's do the photo view. And let's do 3D. Here we go. Do a nice little 3D display. So again, all in the browser. So you can see that I do have like building heights, and there's not a lot of trees in this part of San Francisco, but you can see a few, I think maybe out here. You see some tree height information, but that is in the model, so that's nice. And we are growing our high resolution database in Spectrum-E. So subscribers in time will be able to access more and more of it. We have roughly about 50 cities/airports and different areas around the US and some parts of the UK available. Of course, this isn't available everywhere. So if you are interested in getting high resolution data from us, we can help you obtain that if possible. Or if you have some and you'd like it converted and used for use with Spectrum-E, we can help you with that as well. In time, that may be a lot more contiguous for various parts of the world. All right, so here we go. We have this information, and I have a number of access points littered throughout the area, and they are all at 2.4 gigahertz. This is kind of a simulation of an 802.11 network, and 1 watt power, about 2 to 6 meters in transmit antenna height. So if I select all of them and I decide I want to run a coverage calculation with 1812 model, I can go here and pick my 1812 option. And my options here on my right are kind of a little exclusive to me because I do a lot of presentations. So if you get a subscription, you might not see the exact same options. But if anything here that you see in my demonstration interests you and you want to learn more about it, when you get your trial, or if you already have an access to the tool, just ask us about it and we can let you know if your subscription or your trial covers that, or we can maybe enable that for you. All right, so let's run 1812 model. So here's the input parameters. So we got receive height, calculation distance, and we're going to go about 5 kilometers. Location and time variability. You see the Delta Bullington is the default diffraction recommendation based on the latest revision of the 526. And this is considered generally very optimistic, but that's where we're going to compare with the less optimistic approaches, in particularly the application of the terminal clutter losses. So here is the clutter resolution, and we can here toggle between standard, which would be the default 30 meters that are included globally, or the high res. And the high res option only applies if there is high resolution data available. So the terminal clutter losses, we can apply at the receive position, transmit position, or transmit receive. I'm going to ignore them for the first time out. And then 500 points is enough, considering we're only going to work with medium resolution and only go up 5 kilometers. So this is where I can toggle basically the precision of the calculation. More points, obviously, more precision based on your distance length. I'm going to run it, And it's going to go very quickly, as you can see. We'll see this in a little more detail when I run the high resolution approach, but I very quickly engaged multiple calculation threads, and the coverage calculation completed very fast. But I would assume that it's such a short range. So I can ask to display the coverage in a power received or field strength received or uplink, power flux density, or a variety of display options here. I'm going to go with a power received, and I'll call this 2011 San Fran 1812, and the medium res, no losses. So the no clutter losses. Maybe we should put no C losses. Not going to bother with the gain right now for the receiver. Just apply. So it produces a result. And as you can see here, I have a custom palette. You can customize your result layer. I'm going to switch to my default heat map. And this is my signal strength heat map. This is probably what many of you are more accustomed to seeing, but you can personalize the results how you wish. There's a whole option for creating custom palettes in different units and so forth. So I had another custom one displayed at the moment, but I can always go back to the default heat map view. And so you can see here, this is pretty extensive. You can see this looks like the coverage range would go very far, but keep in mind I am ignoring clutter. So it's really just terrain, so I'm going out like, I guess the main coverage would be probably around 2 to 3 kilometers, but I know, for like, if I were an experienced planner, I would know that's probably unrealistic in an area like as densely urban as San Francisco, is part of urban San Francisco, that my coverage would really go that far. So I can go ahead and try and redo the calculation. And this time I would try the higher resolution data. So I'm going to go run the calculation again. And same parameters, except in the clutter resolution, I'm going to pick the standard option. And I don't need the clutter losses if I have high resolution data available. And I might pump up the results here, let's say 2,000 points maybe. It could be more points of information, just to not take too long, but quick. And you can see I've engaged all the cores, all the available calculation threads in the cloud that are necessary for the network. So it's only 5 stations, so I don't need more than that. But it's allowing me to reduce the computation time, which would be pretty lengthy if you couldn't engage that. So you can see it's a multi-threaded application, and it is reducing the computation time significantly. So that's obviously one advantage if you work off the online mode, is you can use our computational resources to reduce your calculation times. Of course, if you have available computation resources locally, then feel free to download the software and run it locally. So here you go. I've finished my calculation, and I'm going to display the result. Go to talk. Oops, this is the wrong one. I want talk out power C. Let's compare apples to apples. So this is data 2.11, San Fran. What else did we do? I think I did res, and I think that's all I need to put. This is the high res mode. And there we go. We're going to produce the result. So here we go. So this is probably more what I would have expected. This is, as you can see, very different than the other coverage prediction. And this is probably a little more in line with reality, or probably a lot more in line with reality. So the issue is I may not always have this level of fidelity of coverage information available to me. So using medium resolution cartographic data, can I achieve this same level of result? That's a very good question. So the 1812 model seems to allow that. Actually, I wanted to do this 3D view. So if I zoom in at the right level and do the 3D view, I can see why the coverage is diffracting and bending the way. So you see the urban canyons kind of it's using the high-res digital surface model data to create those coverage effects. So if I don't have the 1 meter resolution data, I only have 30 meter. And let's see, let's just take a look at what the 30 meter clutter looks like. Here we go. So how do I get something that's close to what I was able to approximate with the high-res data? So as you can see, this clutter is not bad, this 30 meter clutter, but it's not granular enough to help me model with precision this Wi-Fi network. So the model itself has to make some compensations for that if I'm limited to using 30 meter data. So I'm going to go ahead, switch back. I'm going to go to my map mode. I like this view more so you can see streets and stuff. I'm going to run this again, but this time I'm going to use the terminal clutter losses option. So here I'm going to go leave it at standard medium resolution clutter, except this time I'm going to use at TX on our RX terminal clutter loss option. And so this will make a difference in the calculation, and I will want to see what that looks like. It'll be a little interesting to compare with the high resolution results. So very quickly produce, because it's a lot less points. And then I'm going to display talk out power received. Let's go again, we'll do this 802.11, San Fran. And see. All right, there we go. So it's interesting. It's obviously not nearly as detailed as the high resolution output, but if I were to compare the two, let's do incognito window here. Let's go to Spectrum Center. So I'm going to go ahead and log in. And I'm going to compare some nice things about having a browser-based tool so you can compare results very easily. So I can, with one access, log in more than once. I just can't run anything necessarily in terms of computation. So if I were to run something, it would kind of lock out my other access. So accessing the tool has some limitations if you try to do it multiple users using the same access. You can view information, no problem, but you won't be able to use the tool in the same way. So let's go here, zoom in about here. So I can switch to my prediction history and I can look at the high-res results. And let's collapse this a little bit so it's easier to compare. So obviously this is a much better prediction result. This is probably more in line with reality, but it's very dependent on having that highly granular data available to you. But if we look at the range, it's approximately between 275, 300 meters. And then if I look over here, calculate the range, it's probably a little less, 200, a little over 200 maybe, 200 meters. Oops, I just let go of the mouse. So yeah, a little under 200. Some places a little closer to substitute for high resolution data. But if you don't have high resolution data available, it can be very useful at producing an approximate coverage that may, be the best you could do with the data that you have. And I assume in a lot of cases, you won't have high resolution data available to you. With the heights, that's important with the heights. This is all about having the heights. So you basically need either a handcrafted high resolution data set, or you would need something like a LiDAR scan, which is probably the best thing to get. But those things can be a little time consuming, or if not very expensive to obtain. There are free sources available in certain parts of the world, but many parts of the world there isn't. In some parts of the world, it's maybe even illegal to have that kind of data. So that's basically the conclusion of this presentation. If we're ready for questions, I guess now, Sarah.
That's great. Thank you for that, Daniel. Yeah, we do have a couple of questions that's come in. Just a reminder to people, use that questions toolbar and I'll put the questions directly to Daniel. Okay, so the first question that's come in, how does 1812 compare to, for example, ITUR 525, 526?
Oh, well, we did cover that in the presentation. So we've not done an extensive comparison between the two models, but the main point of difference is that the 1812 is what we call a mixed model. It considers things as granular and deterministic as high resolution LiDAR data without compromising the non-deterministic propagation effects such as location variability, clutter, not clutter, atmospheric effects, things like this. So that is the main difference, I would say, between the two. Whereas the 526 is what we call a very strictly deterministic model. It considers free space loss, diffraction, as obviously it's a strictly diffraction-based recommendation actually. So it's oftentimes referred to 525, 526 because it's the 525 recommendation that describes free space loss. So those two have been commonly implemented into a lot of tools, but they're kind of limited. They can't consider things like atmospheric effects, ducting, troposcatter, or anything like that. So if you try to use it for, let's say, long links or very long range systems, it might have some limitations in that respect. So this is kind of the best of both worlds. Also, the 1812, the way it was described and baseline is the best, one of the best kind of offerings ITU has made in many years. Whereas the 526, it's not really, you don't have like the baselining information available to you from the ITU. You don't have like comparative models and baseline data and verification information and all that sort of stuff that was available from the study group 3. So a lot more effort's been put in there. And also the 526 model, technically, the latest recommendation has changed a little bit. So it's more working with the Delta Bullington model without the clutter loss option. So that is, as we saw earlier, that could be a very, very optimistic output.
That's lovely. Thanks, Daniel. We do have also a question comparing it to the Longley-Rice model in terms of accuracy, usage, etc.
So Longley-Rice, we haven't done like which is better in that sense. It's really something to be done in like a measurement campaign verifying. We're not here to say, you know, one is better than the other. There's certain benefits of the 1812, as I hope to explain in this presentation. It is designed to work with clutter. I guess it's the simplest way for me to say it. Longley-Rice was not necessarily designed to work with clutter. Actually, almost no propagation models that are public were designed to work with clutter. They are usually developed from many years ago, even before the time of modern computing tools. 1812 is a recommendation that was designed for the modern era. It was designed to work with modern computing capabilities. Of course, there are proprietary models that do this as well, but that's the issue. They're proprietary. So you don't know necessarily. They take a little bit of a secret sauce approach. You don't know what those proprietary models are doing necessarily. So from an engineering perspective, it can be a little tricky, or you can make yourself a little too dependent on the vendor if you know, you're doing your work and you don't really know what the tool's been doing, you know, when it produces the results. If you have a discrepancy or a dispute, this may be more important in coordination and regulatory areas. You want to get kind of an apples to apples comparison. So if people are working with a proprietary model, maybe one side doesn't have it because they don't have that tool, that can create a little bit of an issue. So that's one thing. One thing is, yeah, Longley-Rice wasn't designed. We have an implementation that works with clutter data, but it wasn't designed to work with clutter data. Is it more accurate, less accurate? That's up to a measurement campaign to verify. But Longley-Rice is a standard. It's a government standard, so that's has a different effect to you know, your analysis. So you can always rely on that. The code is available online from the NTI ITS website, and you know, it's not it's used by many organizations for broadcasts and stuff. It's a multi-purpose model, so you could use it at elevations that are above 10 meters or anything like 25 meters. So 1812, it's not designed for that. As you saw, the clutter loss options are restricted to certain elevation.
That's great. Thank you, Daniel. Okay, the next question, do keep your questions keep coming in. How does the model behave if there are two or more types of clutter between two antennas? So that's a behavior.
Yeah, that's a good question. So the model, it is, if you have multiple layers of clutter, I believe it considers it at the terminal points. Is that correct, Queenie? The clutter is only considered at the terminal points and also in the profile?
There are like two separate method. One is to include the terminal clutter, which considers the clutter around terminal, and the other is the clutters along the path profile.
Okay. Yeah, so when it calculates the profile, it's putting the receive position, right, at each pixel on the profile. So depending on which option you select, clutter loss is at terminal position or receiver position or both, that's where it's going to apply the clutter loss formula. And so depending what the clutter code is at that position, it will apply. And if your heights meet the criteria, meaning they're inside of the heights that are defined in the table that I highlighted earlier in the PowerPoint part of the presentation, it's going to apply the appropriate losses. So it is. So if you have, let's say, 3 different clutter categories between the transmit and receive position, you have to put the receiver all along the profile to calculate the path loss. So that receiver is going to go through each one of those clutter categories. And then if the receiver is meeting the criteria, the clutter loss model will apply if the user selected to apply it.
That's great. Thank you, Daniel. Thank you, Queenie. Next question. Is it possible to activate and deactivate the stations to see the impact on the coverage without rerunning the composite prediction?
I mean, yeah, you could deactivate the stations. There's options for that. I don't think it's really necessary because you store all the predictions in a history. So I could always just click on one of my previous predictions and I can display it. So I don't have to recalculate anything. So you have a prediction history, it's very convenient, and I can jump back and forth and compare results. If I want to hide these stations, I can do that as well. I can just hide them. If I want to run an analysis but ignore some stations, there is that option as well. So if I turn that back on, I can, if let's say I had 100 stations or something like that, and I only want to run a couple of them, there's a few ways I could do it. I could just pick 2 and run the analysis for those 2, or I could turn some off. So there is an option here. If I were to, let's say, pick let's pick these stations, I want to turn them off. For example, you can go modify selected objects, and then there's an on-off option. I think it's between 1 and 0, and I toggle the setting off. I think is 0. I'll apply that to those stations, so then they won't be considered the next time I do my run. And so I can just do my run. I can do a select all run, but those will be ignored in the calculation. So yeah, you could do that kind of stuff if you wish. Okay.
That's great. Thank you, Daniel. Does 1812 also consider multiple reflections?
Okay, I think I understand. It does consider reflection. If you're taught, it does consider multipath reflection. The 1812 model does not include, if you're talking about like a ray tracing engine. If I'm correct me if I'm wrong, Queenie. I don't think there is, or if that's what you're trying to approach. So it doesn't have that sort of thing. There are other options in Spectrum to model that sort of aspect. It's a very heavy type of computation, but I don't think that's covered by the 1812 model. Am I correct?
Do you mean reflection?
Multipath reflection. So basically, you are considering, as you can see in the result, you are seeing some reflection, but you're not.
Yes.
When I showed you, yeah, you're seeing like it does look at the buildings, and then you are modeling the curving or the canyoning effect, as you can see. It is doing some of that. So that is considering some of the building reflection. But if getting at like a total ray tracing engine, I don't know if that's covered by the 1812 model. I don't believe it is, but we can confirm that later, get back to that question. Yeah, okay, Queenie just confirmed. She's the guru, so she said no, there's no ray tracing engine, but I think this is still pretty good, and especially if you need to consider time. If you want to get into really detailed ray tracing, your computation demands go up substantially, and you're going to wait a lot longer to get the results. So this didn't take very long to produce. It took literally probably 10-15 seconds. So if you imagine to have a very dense network of, let's say you had 1,000 or 5,000 points of presence, trying to run a computation like that with full ray tracing, it could be very time consuming, very, very lengthy.
Thank you, Daniel. Okay, so just for the last question we've got coming at the moment, is the time and location variability percentage always 50-50? So that's the time and location variability percentage.
No, I could change. There's a variable parameters in the tool. So I just didn't change it because I didn't have a need to, but I can put it to 90 if I want, whatever, run it with the criteria I want. I just didn't have a reason to do it. But if you want to increase those are inputs, as we illustrated earlier in the presentation. So you can modify those values. They're not stuck at 50-50. When we did our verification, remember, we did it at 1, 10, and 50% with the MATLAB model. Entry loss considered in the model. It's something that's covered by the 1812, the latest revisions of the 1812, and yes, so that's an affirmative. Building entry loss is covered by the ITU 1812 recommendation. Correct.
Okay, in the absence of any further questions, we're going to finish for today. If you do have any follow-up questions, please, by all means, do email them to us and we'll get back to you by email. For everyone else, first I'd like to say thanks to our presenters. Thank you, Daniel, and thank you, Queenie, for attending today. Thanks, everyone else. Have a great day. Stay safe and stay in touch. We'd hope to hear from you soon. Thank you, everyone.